We saw on the previous screencast that the empirical rule can tell us the percentage of data within 1 standard deviation of the mean, 2 standard deviations of the mean, or 3 standard deviations of the mean. But we also want to be able to find other areas. For example, given a specific spot, we may want to know what's the area under the curve strictly to the left, or given a specific spot, what's the area under the curve to the right, or what's the area between two spots. So we need to be able to find any area underneath of the curve. That is going to be essential. So the question is, how do we get these areas? Lucky for us, mathematicians have already used the equation of the curve, which was that ugly, messy thing with sigma and mu and pi and e in it. They've used that equation and done some integral calculus to find areas underneath the curve. And instead of doing integral calculus, all we have to do is be able to read a standard normal distribution table where the areas will be listed for us. But to get to this table, we need to realize one thing first. Technically, there are infinitely many normal curves. This red curve here has a population mean of whatever that value is. This blue curve has a population mean of whatever that value is. This black curve has a population mean of whatever this value is, and they all have different standard deviations. For example, this blue one here is much more spread out than, say, the red one. So the standard deviation of this blue curve is larger than the standard deviation of this red curve. So essentially, along the number line, there are infinitely many possible normal curves. So we cannot create a table that represents infinitely many curves. So instead, we've got to make this transition from these guys over to here, which this is called the standard normal distribution. And the reason it's called the standard normal distribution is because instead of working specifically with raw data values, we convert everything to standard scores known as z-scores, which we've already studied in the course. And under this transformation from raw data values x to standard scores z's, the areas are preserved as you do this transformation. So what that means is essentially whatever area is to the left under the raw data values, the corresponding z value would have the same area to the left of that. So every single normal distribution curve can be boiled down to the standard normal distribution curve. We then have a table representing the area underneath the standard normal distribution curve. We will see that table in a minute. We need to note a couple of key features of the standard normal distribution curve. Notice that mu is precisely 0. The standard normal distribution has a mean of 0. And right here, which is the inflection point, is a distance from 0 to 1. So the sigma, or the standard deviation, the population standard deviation, is exactly 1. So these are the key features of the standard normal distribution. It has a mean of 0 and a standard deviation of exactly 1. It's also worth noting that, just to connect this to a previous screencast, z-scores above 2 or below -2 are considered unusual. So above 2 or below -2 are considered unusual, and z-scores above 3 or below -3 are considered highly unusual. So above 3 or below -3 are considered highly unusual. Let's now take a look at the standard normal distribution table. You have access to this exact table here. It's much longer than what you see here. This is just a snippet of that table. Since we're dealing with the standard normal distribution, we're dealing with z-scores. So first we need to understand that this column here and this row both represent part of the z-score. And then not in bold, in the heart of the table, these are all areas. All right, so first, let's suppose you had a z-score of 0.34. To locate that specific location, in this column, you've got the ones and tens position, ones and tenths. I'm sorry, I believe I said tens, tenths position. And this over here represents the hundredths position. So the ones and tenths position has the 0.3 in it, and the hundredths position has a 4 in it. So we need to find the 0.3 over here, and this 4 we need to find over here, right? So a z-score of 0.34, we go first to this 0.3 and then go over to the 0.04. So 0.3 plus an additional 400ths would put us at 0.34. And notice the number we get is right here. This number right here represents the area under the standard normal curve specifically to the left of the z-score 0.34. So pictorially, the standard normal distribution again has a mean of 0. So 0.34 would be a bit to the right of that. What this means is the area to the left of that 0.34 is 0.6331. So the key thing that you must note here is that these areas right here are areas to the left of the z-score. This picture suggests that we're talking to the left, not to the right of that z-score. This is just how this table is set up. Other tables are set up where the area is to the right. So you need to remember with our table that these areas in here are areas to the left of the specific z-score. Let us try a specific example. We want to find the area under the standard normal curve to the left of z equals 0.55. And technically, we don't need this graph here, but it can help us visualize what's happening. So z equals 0.55 would correspond to this spot right here. Because again, the mean is 0, and at the inflection point, you'd be over at z equals 1. So we want the area to the left of z equals 0.55. So in our table, again, 0.55, you would find 0.5 in the left-hand column, and then this additional 5 we'd find in this first row. So 0.5 right here, we'd scroll over to where it says 0.05, and we get to this number right here, 0.7088. That is the area to the left of z equals 0.55. So this area in gray here is 0.7088. Again, the total area under this curve is 1 because while it's the standard normal distribution curve, it is a normal distribution curve. So its total area is 1. So this makes sense that you've got 50% over here to the left of 0 and a bit more, putting us at a total of 70.88% of the area underneath of the curve. Here is another example. Find the area under the standard normal curve to the right of z equals 1.19. So we have to be careful here to pay attention to. We want the area to the right of z equals 1.19. So we're still going to look at the table the same way we did before. We need to find the 1.1 in the left column and then the 0.09 in the upper row and find out where those two things intersect. So you got 1.1 is here, the 0.09 is here. We want to see where they intersect. That gives us 0.8830. Now the most common wrong answer is students write down the area is 0.8830. But does that look correct? If this point right here has a z value of 1.19, does it look like 88.3% of the area under the curve is found over here to the right? No, not at all. It looks significantly smaller than that. And the reason is because of this. You have to remember the area underneath the curve that you get in this table is area to the left. We don't want area to the left here. We want the area to the right. So this area of 0.8830 is this area over here to the left of z equals 1.19. Well, we know that the total area under the curve needs to be a total of 1. So if 0.8830 is to the left here, then whatever this is needs to add up to 1. Said differently, if you take the total of 1 and subtract off the area over here of 0.8830, that will give you the area to the right over here. So our answer is 1 minus 0.8830, not 0.8830. And when you subtract these, we get 0.117. So this area under the curve right here is 0.117. And in general, what we did to get the area to the right, we took the whole area, which is 1, and subtracted off the area to the left. So while this table only has areas to the left, we can use this formula here to get areas to the right. We would just take 1 minus the area to the left that you get in the table. Let's look at another example. Here we want to find the area under the standard normal curve between z equals negative 1.5 and z equals 0.82. Notice this time that I did not give you a table. The reason is that I want you to confirm the numbers that you see here in the video by going through the standard normal distribution table on your own. So we want to get this area in here. Well, let's start by noting that this point right here is 0.82. Remember, this axis has z-scores since it's the standard normal curve. And this z-score over here is negative 1.5. So we're looking for this area between these two here. Let's first get the area to the left of 0.82, which won't stop here. It'll continue giving us all this here. And the area to the left of z equals 0.82, according to your table, is 0.7939. That's this area, which includes this piece right here. So 0.7939 is all of this. We don't want this piece over here. We want to get rid of that. Well, that's precisely the area to the left of negative 1.5. Let's find the area to the left of negative 1.5. Now be careful, make sure you realize here that negative 1.5 is the same thing as negative 1.50. So in the left column in your table, you're looking for negative 1.5. In your top row, you're looking for 0.00. And you'll find the area to the left of z equals negative 1.5 is 0.0668. So this area right here, this little piece, is 0.668. And again, this whole thing in blue was 0.7939. So neither of those is our answer. However, if you take all the blue and subtract off this red, then that would give you just this part in gray, which is what we want. So our answer is going to be 0.7939 minus 0.0668, and we get 0.7271. That is the area in gray between z equals negative 1.5 and z equals 0.82. So in summary, if you want area between two z-scores, you get the area to the left of the larger z-score, and you subtract from that the area to the left of the smaller z-score, or lesser z-score. That then gives you the area between. These are all the possible scenarios that you'll have to deal with. You'll need to be able to get area to the left of a z-score, area to the right of a z-score, or the area between two z-scores. Here's a quick summary of how to find those areas. To get the area to the left, you simply take the number that's actually in the table. The numbers in the table are areas to the left. To get the area to the right, you do 1 minus the number that you get in the table. And to get the area between, you take the greater number in the table minus the lesser number in the table to give you the area in between.